Welcome everyone. Today's lesson is entitled Linear Functions Day 2. This obviously follows the Day 1 lesson where we explored the linear function y equals mx plus b. Today's lesson will be predominantly graphing calculator based, where we'll be looking at sets of data and having the graphing calculator come up with a linear model to best fit the data. So a couple things we're going to have to do with our graphing calculators here. Preliminary steps. I kind of wrote this up at the top here. And by the way, I've wrote a variety of things on this sheet that you can reference as you start to do things independently. You'll at least have this as a basis to use. So let's go ahead and start it out here. A couple of these preliminary steps you'll continue to do time and time again, but this third one you're only going to have to do once and then never again. So grab those graphing calculators and let's go to it. So it says first order of business is go to the y equals in the top left. And if you have any equations already in those y equals, if you can clear those out, that would be great. So I'll let you do that. And then in the very next breath, you're going to hit second and y equals. And that's going to take you to this menu right here. And as it says on the sheet, we're going to turn plot 1 on. So I want you to go ahead and hit enter on number 1. And at this time, mine is off, so I'm going to go ahead and highlight on and hit enter on that. And then since we're going to be looking at a scatter plot in 2 variables, that's going to be the one we want. And then make sure this says L1 and L2, and then the mark really doesn't matter there. And just quick for your information on the L1 and L2, if you need to change that for whatever reason, if it's not already L1 and L2, second and the number 1 would be L1, and then second and the number 2 would be L2. Okay, great. Now the third preliminary step says turn diagnostic on, and as it says, we're just going to do this one time and one time only. So I need you to hit second and then the catalog, which is the 0 there. So second and then the 0, and it takes you all the way down there. And you could just start scrolling down to the D's if you really want to. Sometimes you can hit alpha, there it is, alpha, and then find the D, and it just gets you into the D's right away there. But whatever it takes, you're going to just scroll on down until you get to diagnostic on, and there it is right there on my calculator. And then I'm going to hit enter when that is ready to go, and then I'm going to hit enter one more time, and notice it says done. And it's just going to allow some information that we need to come on up. So we turn the diagnostic on in order to do that. And again, once it's on now, we don't have to deal with it again. Now, I actually wrote this right below a couple of the steps that we're going to take here. Troubleshooting a common calculator issue. Now, I've been at this a long time, and there's an issue that just comes up time and time again when working with students. So I want you to be aware of it ahead of time here, just in case it comes up for you, and then you'll know what's going on. So here's what I wrote. If you get an invalid dim, that's what it's going to say. It's short for invalid dimensions, so it should look something like that, invalid dim error message. If you ever get that when working with functions, and you won't get it today because we've got our plot on and we're using it the appropriate way. But if we ever get, or if you ever get an invalid dim error message while graphing a function, so after this lesson, if you kind of just go back and you're graphing things into the y equals and it won't graph and it says invalid dim, chances are it's because of the plots that are on. So let me make sure I put this correctly for you. So if you get an invalid dim error message while graphing a function, let's see, and just turn the plots off. That's the best way I can say it. So if you're not using the plot at that time, just turn them off. So right now for us, we need them on. It's all good. But at some point in time, if you're like just graphing functions normally, you're not doing any scatter plots, turn them off, and then you can avoid getting this invalid dim message. All right. So again, anytime you need help troubleshooting the graphing calculator stuff, I can certainly help with that and fix it in an instant. All right, in the meantime though, we're going to get into our three-step scenario. So really it boils down to three different steps when we want to come up and model data. So we enter the data into the calculator. We're going to view the data on the calculator, and then we're going to have the graphing calculator model the data appropriately with the type of regression that we want. And in this case, we're talking about what's called a linear regression. And so you can kind of see this right here, LINREG, that is shorthand for linear regression. All right, so we enter the data, view the data, model the data. All right, so you're going to access this as best as possible. We're just really going to do one example and kind of go through the motions here, and then you'll obviously try a few on your own. All right, so example one is a good one to start with. So the following table shows the calories burned per minute when walking at 3 miles per hour. So we have 1, 2, 3, 4, 5, 6 sets of ordered pairs, 2 variable quantities, one representing the body weight and the other representing the calories burned. So we talk a lot about this with functions, of course, which depends on which. So out of those two, which would represent the dependent variable quantity and which would represent the independent variable quantity. And the way I would personally phrase it, I would say that the calories burned depends on the body weight. And so what I wrote here, calories burned for the dependent variable. And remember, it's always y depends on x. So that's how we want to think about this. So calories burned would represent the y values, and the body weight in pounds would represent the independent variable denoted by our generic independent variable x. All right, so y depends on x. We've got that all together. And if you want to go ahead and put that up here, that's fine with me. Doesn't really matter. Again, just always what you want to do initially is decide which depends on which, and it's always y depends on x. All right, so part B, use the calculator to make a scatter plot of the data. So this goes into our step 1, everybody. Enter the data in the calculator. So as it should say on your sheet, to enter the data, we hit the Stat button right up here next to the arrows. And let me get that going for you. There we go. And we go into Edit. So it's the very first one. Now, if you have data in here, I'm going to show you how to clear it out. In fact, it says it on your sheet. But you're going to go up to L1. So I pressed the up arrow and got up there, and I'm going to hit Clear and then Enter. And then if I had any data there, it would have disappeared. So if you have any data in L2, what you're going to do for me is go up to L2, just like I did there, and I'm going to hit Clear and then Enter. Okay, and that should clear out any data that is potentially in there already, and now we can start from scratch. So you're probably going to be a lot quicker than I am here, but we're going to enter the data in at this point. So remember, X's are the L1, so the body weights in this particular case. All right, so I have my 6 independent variable values in. I'm going to move it now on over using the right arrow and get over there, and we want to match this up perfectly. So I've got my 2.7, and again, you guys are, I'm sure, quicker than I am here. Getting closer there. All right, so data is in. Step 1 completed. Now what we want to do is see the data on the scatter plot there. And so the nice thing about these graphing calculators is they will provide you with an optimal window for this particular set of data. And so what you're going to do is everybody hit zoom at the very top. And again, it says it all on your sheet here if I go too quickly for you. And you can just hit number 9 if you want. I'm going to just scroll on down to show you what number 9 is, but you can really just hit number 9. And it's the zoom stat window. So again, it is a window that will give us the perfect scatter plot window for the data that we entered. So I go ahead and notice we get our 6 ordered pairs plotted on the coordinate plane using the marks that I had denoted in the menu initially. All right, now I'm going to go ahead and just hit window. You do not have to do this, but if you kind of take a look, it shows you that the body weights are going from 88 to 232, and the calories burned are going from like 2.1 to about 6.4. So again, it selected those in order to get us a good visual and have all the points on the appropriate window. All right, so now we're looking pretty good, and you can see as we start to investigate this pattern of data, it certainly looks quite linear, and so it allows us to put a line in place to fit that set of data. So then we go to part C, and it says, find a linear regression. So once we acknowledge the fact that the pattern formed is linear in nature, we're going to come up with a linear regression for the data. So all types of regressions we're going to see over the course of this year. For this, obviously, it's going to be linear. And so the way we do this, of course, is you hit the Stats button for me again, and you're going to move it over 1 to the right, over to Calc, and you'll see a variety of regressions as you get a little further down. Again, we are going to hit number 4 there. I just want you to see a couple of the other ones initially. So there's quadratic and cubic and quartic, another type of linear, what's called logarithmic, exponential, a power regression, logistic, and what's called sinusoidal. So all different types of regressions based on the patterns of data that we will see. But for our purposes here today, we just need to go to number 4, and that is the linear regression right here. So you're going to hit that, and then we're going to pause for just a moment. Now, if you have a TI-83, your calculator will look just like this, and I'll show you what to do in just a second. If you have a TI-84, yours looks a little differently, and that's okay. So at this stage, we're going to do something just a little above and beyond here. It's not a true necessity. So for all of us, like for those that have a TI-83, if I went and hit enter right now, it would give me the regression that I need, and that's great. For those that have a TI-84, you would scroll down to where it says calculate, and you would hit enter on that, and again, it would give us the regression. We're going to do something a little bit before that though, and again, it's different on the 83 than on the 84. So if you have an 83, you're just going to do it right here. If you have an 84, and it says this on your sheet, it says scroll down to store regression equation. Just go right down to that one, and then have your cursor there, and then you're going to do exactly what I do on my 83. So you went down to store regression equation, and now we're going to hit the vars button. We're going to go over to yvars. We're going to hit function, and we're going to throw this into y1. And so what we're telling the calculator to do is to store the calculated linear regression into the y equals, specifically the y1. So it can graph the equation along with the data on the screen that we saw just before. Okay, now everybody, 84 calculators, just go down to calculate and hit enter. 83s, just hit enter. And you see that we have our y equals, and they have just the generic a and b right here. Numbers will go in just a second. This will represent our slope. This will represent our y-intercept, and it's meant to be a best fit model for the data that formed a linear pattern on the coordinate plane. So in terms of find a linear regression, it says round to 3 decimal places, so I have y equals 0.027x minus 0.017. Awesome. Let's move on to the next piece. So you noticed another thing that came up there. In fact, I'm going to bring my calculator up just so I have it. Notice this r squared and r. For our purposes here, everybody, we're just going to focus on the bottom one where it says r. And by the way, that's why we turned the diagnostic on, so it could show us this particular value. So anyway, I'm going to read just from the paper and kind of go from there. It says the correlation coefficient, which is the r value, is a statistic that illustrates how well the line of best fit represents the data. The closer that the absolute value of r is to 1, the more perfect the linear relationship is. So I just copied a couple on here so you can kind of see. If they are perfectly on a line, then you will get an r value of positive 1. And by the way, inclining relationship, you will have a positive r value. But if you notice values that decrease from left to right, you would have a negative r value. So you could see this one, it's a strong linear correlation, and it is declining. And so you're going to have an r value close to -1, whereas that same type of association, but is increasing from left to right, would be positive. Okay, and then obviously one that has a weak or really no association whatsoever, you're going to see an r value closer and closer to 0. So in this particular case, it looks like going out several decimal places, I got 0.99978. So this statistic tells us that our data was very, very linear, and that we can be pretty confident in our regression to fit this data. All right. Very good. So we have our regression, and that's great. We're going to use it to make a prediction in just a couple minutes. But one of the things we talked about in the previous lesson was slope. What is its context? And in very broad terms, I just talked about slope means the rate of change. Remember, change in y per change in x. So what I want you to do is literally just take a moment, and I want you to write down what you think the slope means within the context of this problem, and then I'll write down what I have, and you can see kind of how closely you worded it to what I worded it as. But I would love for you to try to give this one a try on your own. Okay, so let's see what you wrote here. So I've got, it is the increase, because it is a positive slope. So this is how at least I interpret it. It's the increase in the number of calories burned and we want to be as comprehensive with our definition here as possible. So increase in the number of calories burned per minute, right, because that's what that value represented, when walking 3 miles per hour So it's the increase, and here's where I think it is very important, for each additional, that's the key. It's not per pound of body weight. We're not dividing by the body weight. It's the increase in the number of calories burned every time we add an additional pound to the body weight. So for each additional pound of body weight. So this is just where we have to be a little careful. It's change in y per change in x. That's where the additional comes in. It's not change in y per x. It's change in y per change in x. And so that's why we needed this word. I think that sort of is the big one right there. So you can just take a look how I wrote it, see how it coalesces with what you wrote, but that should make pretty good sense. So every time a person gains an additional pound, they're going to burn that many more calories per minute walking 3 miles per hour. Okay, let's move on. So F and G. So the whole reason for coming up with a model was to make predictions for the model. And so I put 2 buzzwords in place here, and I want you to underline them, please, if you would. And then we'll go ahead and use the models here in just a second. So it's letter F. It says use the equation to interpolate the calories burned per minute if a person weighs 159 pounds. All right, so given one value, use the model to find the other value. So what we have to decide first and foremost is that does that 159 pounds represent the independent variable, x, or the dependent variable, y? And obviously we kind of saw this already from before, but the weight, of course, would be the x value. And so what I have is this would be 0.027 times 159, so that 159 replaces our x, minus 0.017. So given an x value, we should be able to calculate a y value. So I'm just going to go to my calculator, and I'm going to do that exact calculation. And you do the same if you would, please. And it looks like we would get 4.276. All right, so again, using the equation to interpolate, so this would be the calories burned per minute for a person weighing 159 pounds. Okay, awesome. Now, let's go to letter G. So it says use the equation to extrapolate the calories burned per minute if a person weighs 250 pounds. So notice the premise is basically the same. We're making a prediction. I've given a body weight. We're going to come up with the calories burned per minute walking, and we'll go from there. So let's go ahead and throw this into the mix. So I have y equals 0.027 times 250 minus the 0.017, looking good. And I'm going to go ahead and let the calculator do the work right here. So 0.027 times 250 minus 0.017. And I'm going to hit enter, and it looks like I get 6.733. Awesome. So you can see, obviously, a person weighing more has to work harder, and so is going to burn more calories per minute walking 3 miles per hour. Now, here's obviously the big question. I did the exact same math, right? I created a prediction of the calories burned based on a given body weight. So the question is really, why did I use two different terms for that? Why did we interpolate when I asked for 159 pounds and extrapolate when I used the value of 250 pounds? So letter H, it says, what is the difference between interpolation and extrapolation? And, just using this part of it, inter and extra. Inter means within, extra means outside. And so hopefully this kind of came to you. But interpolation is within the bounds of the data. Whereas extrapolation, and I just have a little dash right there, extrapolation is outside the bounds of the data. And I'm just going to bring up the data set just a sec here. So they're both predictions, of course. One is interpolation, one extrapolation. And the reason, let's make sure we get that data. So 159 pounds, as you can see, is within the bounds of the data, going from 100 to 220 pounds. So that 159 pounds is within that bound. But the 250 pounds, as you can see, is outside the bounds of the data. So it obviously kind of begs the very last question up there. And so let me bring it up one more time. Which would you consider to be more reliable, interpolation or extrapolation? And I'm hoping you would agree interpolation would be the more predictable of the two, as we already see the pattern within the bound of within the set of data, but outside the bounds of the data, we don't know if the pattern continues. So we don't know after 220 pounds, which was the last body weight in our data set, if the pattern somehow changes in some way, shape, or form, and it's not as linear, and it wouldn't match and then the model that we used wouldn't be quite as reliable. So interpolation certainly more reliable than extrapolation. All right, last thing just I wanted to show you on the graphing calculator, and we'll wrap this on up and it'll give you the opportunity to work on some of these on your own. So we put all the data in, remember that? So we have that right there. And go ahead and hit your y equals, as I just did. And remember what we did? We stored the regression equation into y1. So you see that rather than us having to kind of paste it in manually and type everything in, it did it for us. And the nice thing is if I hit graph, now we also see that same line show up matching our set of data on the scatter plot. And you can see how well that line of best fit does really correlate with the data set that we have in place. So again, just wanted you to see that. That's why when we did our linear regression, we stored the regression equation into y1 and allowed us to kind of see the model with the data. Is it absolutely mandatory to do that? No, as I mentioned, but not a bad habit to kind of develop as you do a lot of different data sets and a lot of different models and stuff. All righty, everyone, I'll stop right there. I can, again, troubleshoot any of these calculator issues that come up, so please don't hesitate to ask. And, you know, just do the best you can with the technology. And if you have questions, do let me know. Thank you.